Classical physics is dominated by two fundamental concepts. The first is the concept of a particle, a discrete entity with a definite position and momentum, which moves in accordance with the Newton's law of motion. The second is the concept of electromagnetic wave, an extended physical entity with a presence at every point in space that is provided by electric and magnetic fields, which change in accordance with Maxwell's law of electromagnetism. The classical word picture is neat and tidy. The law of particle motion account for the material world around us, and the laws of electromagnetic fields account for the light waves which illuminate this world. This classical picture began to crumble in 1900 when Max Planck published a theory of blackbody radiation, that is, a theory of thermal radiations in equilibrium. With a perfectly absorbing body, Planck provided an explanation of the absorbed properties of blackbody radiations by assuming that atoms emit and absorb discrete quanta of radiations with energy E is equal to h nu, where nu is the frequency of the radiation and h is a fundamental constant of nature with value 6.62 multiplied by 10 raised power minus 34 joule/second, where h is also called Planck constant. We shall see that Planck constant has a strange role of linking wave-like and particle-like properties. In so doing, it reveals that physics cannot be based on two distinct, unrelated concepts, the concept of a particle and the concept of a wave. These classical concepts, it seems, are at best approximation description of reality. Photons are particle-like quanta of electromagnetic radiation. They travel at the speed of light c with momentum p and energy c, which is given by p is equal to h over lambda and E is equal to hc over lambda, where lambda is the wavelength of electromagnetic radiation. In comparison with macroscopic standards, the momentum and energy of photons are tiny. The evidence for the existence of photons emerged during the early years of the 20th century. In 1923, the evidence became compelling when A.H. Compton showed that the wavelength of an X-ray increases when it is scattered by an atomic electron. This effect, which is now called the Compton effect, can be understood by assuming that the scattering process is a photon-electron collision in which energy and momentum are conserved. As illustrated in the next figure, the incident photon transfer momentum to a stationary electron, so that the scattered photons has a lower momentum and hence a longer wavelength. In fact, when the photons is scattered through an angle theta by a stationary electron of mass me, the increase in wavelength is given by delta lambda is equal to h over mec into 1 minus cos theta. In this figure, you can see that the initial momentum of the electron is pi. When this electron is collided with photons, then after colliding, the momentum of the electrons will be pf, which is the final momentum, since it is scattered through an angle theta, you can see in the figure. The concept of a photon provides a natural explanation of the Compton effect and of other particles like electromagnetic phenomena such as the photoelectric effect. However, it is not clear how the photon can account for the wave-like properties of electromagnetic radiations. We shall illustrate the difficulties by considering the two-slit interference experiment, which was first published by Thomas Young in 1801 to measure the wavelength of light. The essential element of a two-slit interference are also shown in the next figure. When electromagnetic radiation passes through the two slits, it forms a pattern of interference fringes on a screen. These fringes arise because wave-like disturbance from each slit interference constructively or destructively when they arrive at the screen, but a close examination of the interference patterns reveals that it is the result of innumerable photons which arrive at different points on the screen. You will see that when the intensity of light is very low, the interference pattern builds up slowly as photons arrive one by one at random. When photons arrived one by one at random points on the screen after seemingly passing through both slits in a wave-like way, These photons are not behaving like classical particles with well-defined trajectories. Instead, when presented with two possible trajectories, one for each slit, they seem to pass along with trajectories, arrive at a random point on the screen, and build up an interference pattern. De Broglie wave. The possibility that particles of matter like an electron could be both particle-like and wave-like was first proposed by Louis de Broglie in 1923. Specifically, he proposed that a particle of matter with momentum p could act as a wavelength. Lambda is equal to h over p. This wavelength is now called the de Broglie wavelength. Indeed, the first experiments to demonstrate the wave properties of electrons were crystal diffraction experiments by C.J. Davison and L.H. Gormer and by G.B. Thomson in 1927. Davison's experiments involve electrons with energy around 54 electron volt and wavelength 0.17 nanometer, which were diffracted by the regular array of atoms on the surface of a crystal of nickel. In Thomas experiments, electrons with energy around 40 kilo electron volt and wavelength 0.006 nanometer were passed through a polycrystalline target and diffracted by a randomly oriented microcrystal. These experiments showed beyond doubt that electrons can behave like waves with a wavelength given by the de Broglie.